Hey, what's up, guys? Yeah, today I want to present some moment methods, basically moment method inequality and probability. So basically, there's many inequality in the probability theory. For example, like the Markovian inequality, Chebyshev inequality, and the Chernoff bonds. So there are there are some of them. The first one is Markovian, and the second is the Chebyshev, and the Chernoff bonds. Okay, and three of them are basically connect so-called moment method. So I will present their proof and the application in this video. So if you learn some more advanced probability inequality, then you can start from it. Hope you guys subscribe to my channel. Okay, so let me just quickly start the proof. Okay, so let me just quickly introduce the notation, right? Because in the probability video, that in the probability case that everybody use a different notation. Okay, so my expectation value E of x is defined to be, let's say you take x, which is a random variable, and you take your random variable x is let's say small equal to x, right? So this is the expectation value, and the variance of x is defined to be the expectation value of the x squared minus expectation of x squared. Okay, so these are common variable. And the one you can use the characteristic function. So now we are in the more advanced idea that we use major theory, right? So there's no difference between continuous and discrete. So this IE means that the characteristic, or the characteristic function on event E. Okay, so if you take the expectation of this event E, it gives you the probability of E. Okay, so this is a bad notation, right? But this is expectation value. Okay, and then for each where occurs the function, which is also a random variable, that you get the probability E of the probability E squared. Okay. Okay, I think this is enough. Okay, so let's start the first one. So this is the first moment method. Okay, so let me just quickly say. So this is the first moment. So the first moment means that suppose you know the expectation value of your random variable, then how can you use your expectation value random variable to control the probability? So that means you know that the ex is less than infinity, and you want to use the probability, the expectation of x to control probability. And the Chebyshev is the second moment method. So second moment, the idea is that suppose you know ex and the ex squared, then how can you use the expectation value of these two to control the probability? And the Chernoff is basically an exponential method, or you can view as higher moment. And this idea are commonly used in the analytic number theory probability. Okay, so the starting point is that your random variable is greater or equal to 0, means that their results must be non-negative, and the Markovian inequality basically says that probability of x greater or equal to lambda is less or equal to 1 over lambda expectation of x. Right, so this is the first moment. Suppose you know the first moment, then you can use the first moment to bound the probability. Okay, so proof. If you start from the undergraduate, then maybe you will write the integral and try to bound it, right? But in this more advanced idea that one can quickly prove it by using definition. So notice that for each you will have this, right? So for each random variable greater or equal to lambda, this is characteristic 0, right? So when x greater or equal to lambda, then left hand side is okay. So let me just write when x greater or equal to lambda, then this equality holds, right? Because left hand side is lambda and the right hand side is not left hand side greater than lambda and the right hand side equal to lambda. When x less than lambda, then this is still positive because my non-negative because this is my assumption, and the left hand side becomes 0, right? So you get this and you take expectation value, right? So you get E of x greater or equal to lambda, and then you take expectation value of these events, give you the probability of this, right? So you can easily prove this. Okay, so this is the Markovian inequality, which is a very advanced proof that you're just using the major theory. Okay, so one applications. There are many applications of the Markovian, right? But I want to talk about this. It's very interesting This is called Borel Cantelli lemma. Okay, so the idea is that suppose you got E1, E2, which is a sequence of events, and they can be infinite or can be infinite or dependent, and such that let's say you are very crazy. You take all the probabilities or sum from infinity, and suppose this less than infinity. At least it's a very powerful idea that that in the probability theory that you come up with, you just take sum of all the probabilities of some events, and you can use this to bound some things. Suppose you get this, and then you can ask what is the probability of the how many events happen, right? So you can ask the probability of fewer than, I should say, fewer than m events happens. Okay, which is greater or equal to 1 minus probability p en, and use summation n from 1 to actually greater or equal to 1 from 1 minus the summation of these probabilities. Let's say I from 1 to infinity divided by n. Okay, so that means if this is finite, if this is finite, then you get some bound for you get some lower bound for this type of for this type of inequality. Okay, so proof is very trivial, right? Just so what you do, right? You take, so the idea is that you just take an expectation value on each event, right? So you take a characteristic function on each event. Okay, and you do a summation, right? So this will give you the summation of the probabilities of this. Okay, so once you have this, then you apply the Markovian inequality, right? So you can, so your probability of the events greater or equal to m. There are several all events greater the number of events greater or equal to n. By Markovian equality is less than or equals to probabilities of en, where you sum over this divided by m. So the probabilities of fewer than m is just 1 minus, is greater or equal to 1 minus summation p en, and from 1 to infinity divided by m. Okay, so we prove this this Borel Cantelli lemma. Okay, so let's talk about second moment. Okay, so second moment is a Chebyshev inequality, which is also famous. So let me just write down. So let's say you know x minus. Suppose you want to ask what is the probability that x minus e of x greater or equal to, let's say, lambda sigma, where sigma this sigma is the variance. The sigma square is a variance. Okay, so this is the e of variance of x, which is defined to be e of x squared minus e of x squared. Okay. Okay, so this is for positive lambda, right? So this is that 1 over lambda squared. Okay. Okay, so that means that if you give me some probability distribution, then the probability that the events outside of two times the standard deviation or less or equal to 1 divided by 4. Okay. So this is the second moment, right? So proof is also simple. Just apply the Markovian, right? So you can just use px minus e of x, which is events, right? Greater or equal to square, where lambda square is sigma square, or less or equal to expectation value of this x minus e of x square. So this is a Markovian divided by lambda square sigma square. Okay, so this is definition, right? Because sigma square is defined to be the expectation value of this, so it's 1 over lambda square. Okay, so this is the second moment method that you can use. So this is the idea is that suppose you know the second moment, right? So you can use the second moment to bound the probability. Okay, and this idea, this Chebyshev inequality also have applications, but I'm not gonna talk about this because this is I think you can check the analytic number theory videos or my some of my probability videos. There's many applications that you can start from here. Okay, so the third one, which is the exponential method, which you can prove you can get an idea of using some idea of Chernoff bounds, which is a very, I mean, strange idea. Okay, so suppose you know the every moment, right? Not now, now just e of x, you get e of x squared or something like this, right? So you can want to bound these type of things. Then you can see this is just the same as exponential this, right? So let's say you take some t, I take some t. Okay, so by the Markovian, you can this. Right, you get this, right? So now if you can do an expansion, right? So if you know the higher moment, then you can this expansion, you know all the higher moments, then you start from this expansion, then you can bound this probability distribution by using this idea. Okay, so you can just keep going, right? So but one standard yeah, so this idea is basically Chernoff bounds. This is the final results. Okay, but you can do some simple case. So let's maybe do some simple case. This example is that suppose you got some random variable x, which is less or equal to 1, and you know that which is you shift it mean to be 0, and you take a t from 1 to -1, and you can prove that this is a lemma. That very simple expectation of value of exponential tx less or equal to exponential t square variance of x. Okay. That's the proof. Right, so proof idea is that you using this inequality. So you get 1 plus tx plus t square x squared, and then you take the expectation value, right? So this is a 1, right? 1, and then this is 0 because e of x is 0. So you get the expectation, you get a t square x squared. Okay, and then this is just variance, right? So you get 1 plus t squared variance of x, and then you use the Bernoulli inequality. So remember Bernoulli inequality tell you that 1 plus x, that's equal to exponential x. Okay, so you can pull everything, go to the exponential. Okay, so this is a simple lemma. Okay, so now we get let's go to the final results. This is the Chernoff inequalities. Okay, so these inequalities I haven't put my previous video list because I think it's a little bit hard to say. Okay, but now we already have all the tools, so we can do something interesting. Okay, so it's assumption. So let's assume that we get x1, x2, which is independent. So they are independent random variable, and suppose that you get the expectation value of you can control this type of terms. Suppose this is, let's say, 1 for all I, and you want to do the large behavior. Okay, so x1 up to let's say xn, and you define sigma to be a variance of x. Okay, so this is okay, x, right? Then for all lambda greater than 0, then you got the probability of x greater than e of x greater than lambda sigma greater than lambda sigma is less or equal to 2 of the max exponential minus lambda squared divided by 4 expectation value exponential of minus lambda sigma divided by 2. Okay, so this is the Chernoff inequality. So one example of Chernoff inequality. Usually, the idea is that you come up with some expectation value inequality, and after that you just do the derivative and try to minimize or maximize the right hand side. This is the standard idea that you can come up with the different probability inequality. Okay, so okay, so let me just quickly prove it. Oh, okay. Okay, so in order to do this, then we can okay, so I mean we can just assume, we can just shift it, right? So I can just assume ESI 0 for I. Okay, and you note it, and now I come up with x greater equal to minus lambda sigma is a probability of x greater equal to lambda sigma plus probability of x less or equal to negative lambda sigma. Okay, so I just need to, because this is symmetry, right? So I just need to prove this. I just need to prove this one. Okay, so this is what I just need to prove. Okay, so the idea is very simple, right? So I have x sigma, well, let's equal to x minus exponential t lambda sigma. So this is the Markovian inequality, and the probability, the expectation value of the expectation of x, exponential x, right? So here comes the trick that there are these things that are independent, right? So you can take out, you can just multiply it out. I think even though they are not independent, you can still multiply it out, right? And then you can separate this in exponential, right? Since they are independent, so expectation value of this exponential tx1 times up to like txn is basically exactly the same as expectation value of exponential tx1, exponential tx2, up to exponential txn. Okay, so this is bounded by the previous idea, right? So I proved that expectation value of this exponential tx is equal to exponential t squared variance of x. Okay, so you get the exponential t squared, right? So variance of x1 plus variance of x2 of the variance of xn, and then which is exponential t squared and the total variance of x, since they are independent. So this is exactly exponential t squared sigma squared. Okay, so combine these times these, right? I get the probability of x squared equal to lambda sigma less or equal to exponential minus t lambda sigma exponential t squared sigma squared. Okay, so this is the final results, right? And then you just do the minimization of t, right? You just do it, right? So this is a square of the quadratic form of t, right? So you just do a minimization of t, then you get the you can get these results, right? Because you get this term and compared, you can combine these two. Okay, so this is the idea of the idea of the moment method application in probability theory, and you can start here and prove these three inequalities. And then once you have these three inequalities, then we study more advanced inequalities in the future. Hope you guys subscribe to my channel. See you. Bye.